Acid-base strengths. Strong acids ionize completely in water, so there are 0 molecules of the acid in solution. The concentration of hydronium ions in a dilute solution is equal to the concentration of the acid. So here I've got some equations to represent this. I've used any acid to be represented by HA. So this just means an acid. A for acid, H for the proton that it donates. So the very first reaction here, this very first reaction, is an example of a formal ionization of a strong acid. So strong acids have a single arrow because this reaction goes to completion. So some acid plus water makes the hydronium ion and then the conjugate base, the anion from the acid. The informal way of writing this is just to omit the water. So you've got some acid and it will produce the hydrogen ion and then the anion from the acid, so the conjugate base of the acid. There are only 6 strong acids. The rest are moderately strong or weak. 6 strong acids: hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, and perchloric acids. So this is an example of one of those acids. So sulfuric acid plus water will produce the hydronium ion and then the hydrogen sulfate ion. So we removed an H because acids are proton donors, so it donated the H to the water, so the water acts as a base. And then we produced the hydronium ion and then the anion that is left from our acid, the conjugate base. Informal sulfuric acid ionizes 100% to produce a proton and its conjugate base, or the conjugate base of the acid, the anion that is left after you remove the H+. Weak acids will ionize slightly in water. Most molecules will stay intact and they are in equilibrium with its ions. The concentration of hydronium ions in a dilute solution is always less than the concentration of the acid. So little ionization occurs. So therefore, with weak acids, we have the equilibrium arrows. So some acid plus water will produce a hydronium ion and the conjugate base, the negative ion that's left from the acid. So that's the formal formula. Here we have some acid, it's in equilibrium, so it's a weak acid. We'll produce a proton and the remaining anion from the acid, the conjugate base. So formal, informal. There are many weak acids, and the most commonly used weak acid is acetic acid. So this is, we know it as vinegar. So acetic acid plus water will form the hydronium ion, double arrows, and the acetate ion. So the acetate ion is the conjugate base of the acetic acid. So that's formal. Informal, just you have acetic acid, equilibrium arrows, proton, acetate ion. You can write it either way. Both are acceptable. A little review about acids and bases. So a monoprotic acid means that your acid produces only one acidic hydrogen. For instance, hydrochloric acid has only one H in its formula. A diprotic acid produces 2 acidic hydrogens, but not in the same step. An example of this is H2SO4. And the strength of each step becomes weaker and weaker. So while sulfuric acid, H2SO4, is a strong acid, HSO4 -1 is not. So the conjugate base of sulfuric acid can act as an acid, but it is a weaker acid. Triprotic acids produce 3. An example of this is phosphoric acid. And again, each subsequent acid is weaker. So we have H2PO4 and then HPO4 2-. So each one of these 3 species can act as an acid, but they're weaker than the original acid. So HPO4 2- is weaker than H2PO4 1-, which is weaker than H3PO4. A little nomenclature review. Binary acids contain only 2 elements, hydrogen and a nonmetal. And the naming, you have the prefix hydro followed by the nonmetal root of the nonmetal, followed by ic and acid. So HF, hydrofluoric acid, hydrofluoric acid. HI, hydro, and it's iodine, so it's iodo, and then it's dic acid, so hydroiodic acid. An oxoacid is an acid formed from a polyatomic ion containing H, O, and another nonmetal. So this is our polyatomic ions. If you're an 8 ion, you become an ic acid. So nitrate becomes nitric, sulfate becomes sulfuric, ite ions become us acids. So nitrite becomes nitrous acid, sulfite becomes sulfurous acid. Hypo and per remain part of the acid names for our halogens. So perchlorate ion becomes perchloric acid. Hypochlorite becomes hypochlorous acid. Bases. Strong bases dissociate completely in water. The concentration of hydroxide ions in a dilute solution of a strong base is equal to the concentration of the base. So if I have 0.1 mole per liter sodium hydroxide, I have 0.1 mole per liter hydroxide. Alkali hydroxides, so group 1 and group 2 alkaline earth metals, are considered to be strong bases. Weak bases will ionize or dissociate if they're already ionic. So let's say we have ammonium hydroxide. That's ionic. So that will dissociate. However, if it's covalently bonded like ammonia, it ionizes. But anyway, they only partially ionize or dissociate in water. The concentration of the hydroxide of a dilute solution is always less than the concentration of the base. So for these, we have, again, the double equilibrium arrows. And ammonia plus water produces the ammonium ion and the hydroxide ion. Ammonia here accepted a hydrogen. Going left to right, it accepted a hydrogen, so that's the base. The water acts as the acid because it donates the H plus to the ammonia. So that makes ammonia and ammonium conjugate acid-base partners, base conjugate acid, and that means water and hydroxide are conjugate acid-base partners too. Acid, conjugate base. With the weak bases, you do have to do the water in there. because there's no place for the H plus to come from otherwise. Okay, some definitions here. Strong and weak are sometimes confused with dilute and concentrated. One is a measure of ionization. The other is a measure of the amount of solute in water, so the amount of your acid and base in water. So if I draw a beaker, and I have in it a strong acid, I could do a strong base as well. The concept is the same. I would have a whole bunch of ions. No molecules whatsoever, because all of the HA split up into ions. But I would have an equal number of H pluses as A minus. A weak acid, on the other hand, and the same thing would happen for a base. I would have a lot of molecules of acid and a few ions. So we can see that very little ionization has taken place. Now, concentrated versus dilute. If I have a concentrated solution of either one of these acids, so let's say I've got a weak acid, so we've got a concentrated, weak acid, then I would have a lot of particles, because there's a lot of my acid in my water, but not very many of them are ionized. If I have a dilute, I could have a dilute strong or a dilute weak, but we'll go with dilute weak to be consistent. That means I have very few particles of acid in my beaker or my container. So concentrated and dilute talks about the amount of solutes, the amount of particles in a given volume. Strong and weak talks about how much has ionized, how many have formed ions. Okay, the equilibrium position of an acid-base reaction. Acid-base reactions involve two conjugate acid-base pairs. The shift in equilibrium will be towards the weaker acid and base. So the stronger the acid, it will move towards the side with the weaker acid. So identify the acids in the equation and compare the strengths. So there's tables of acid strengths. So scientists have done lots and lots of chemical reactions comparing acids and bases, and that information is now compiled in data tables. So you would compare the acids that you identify in your reaction, compare them in a strength of acid base compounds, and then this equilibrium will shift away from the strong acid. So you would increase the amount of weak acid. So let's do an example. Hydrochloric acid plus water produces the hydronium ion and the chloride ion. Well, our acids are HCl and the hydronium ion. Now, the hydrochloric acid is stronger than the hydronium ion, so there will be a shift towards the right. And we know this because it's a single arrow. So it will shift away from the strong acid towards the weaker acid. All right, example number 2. Hydrofluoric acid. It's nice that the name actually tells you. Ammonia, ammonium, and fluoride. Ammonium will give up an H+, it will donate an H+, so that is the other acid. If you look in a table of acid strengths, you will see that HF is stronger than the ammonium ion. So the equilibrium will shift to the right for this reaction. So you will have more ammonium and fluoride produced than HF and ammonia. So there's a shift to the right. Next example, we've got sulfate plus acetic acid, and then we've got hydrogen sulfate and acetate. Your acids have to include an H because they're proton donors. So if you can pair acetic acid and hydrogen sulfate is actually a stronger acid. So in this case, the equilibrium lies to the left, so it will shift to the left. So you will have more sulfate and acetic acid at equilibrium than hydrogen sulfate and acetate ions. There's 2 values that can be used to represent strength of an acid or a base. Percent ionization or dissociation. This is used to express how much an acid or a base ionizes or dissociates. For example, a strong acid is always 100%. Less than that, and you've got moderate or weak. So you take the percent ionization, to figure it out, you take the hydrogen ion concentration, so the amount that's ionized, over the initial, and you multiply by 100%. So let's say the pH of an acid is, 5.8. pH is 5.8. The initial concentration is 0.10 mole per liter. So if we have pH, we can find H+. 10 to the negative pH will give us our hydrogen ion concentration. 10 to the negative 5.8. If you end up with a very large number, you forgot to put in this negative. So this is 1.6 times 10 to the negative 6 mole per liter. There should be one significant digit because of the 1 decimal place, but I'm going to carry 2 because this is an intermediate calculation. If I was going to round this off to just the hydrogen ion concentration, it would be 2 times 10 to the negative 6. So if I put 1.6 times 10 to the negative 6 over 0.1, moles per liter cancel, multiply that by 100%, this acid ionized 0.0016%. A lot less than 1%. So this gives you an indication. Percent ionization gives you basically how weak of an acid is. That's a pretty weak acid. Only basically 0.002% ionizes. Your Ka, your acid dissociation constant, also gives you some information. It's just like any other K. You set it up the same way, except we give it an A now for acid, so Ka. So our equilibrium expression If we're doing a formal reaction, will be the aqueous. Your water becomes part of your Ka constant. So this is your Ka expression. If you were going to do informal, it would be H plus A minus over HA concentrations. Okay, so your Ka value is also an indication of how strong something is. For acids, it's basically greater than 1. And you'll see it sometimes in a reference table. The Ka is very larger than 1 for strong acids. And then, I don't know, times 10 to the negative 3, times 10 to the negative 4. Values are your moderate, and then you've got your weaker acids with smaller Kas. So your Ka and your percent ionization are an indication of how strong or weak your acids are.